This is Group 11. My name is Arav Tyagi, and we made the Morse Code Decoder. So, on our FPGA, up on the top, we have the dot button. So when you press that, it'll register as a dot. Then we have the dash over here, and this button to the left is the character end. So when you click that, then our program will actually process what the users inputted through these two buttons and then display something through the VGA on the display. And then down here on the bottom right, we have the reset. So when you switch that switch, then it'll reset the display.
Hello, my name is Karim Elzokm. I'm going to run through the basic functionality of our project. So firstly, here is the library for the Morse code numbers and letters. Now I will attempt just to write hello.
We were also able to display numbers on our Morse Code Decoder, so Karim will go ahead and show a demonstration of this feature.
Hi, Karim with you here. I'm gonna talk you through our code for the Morse decoder. So first we have the inputs, which are clock, reset, dot, dash, char, end, and our outputs, the 8-bit hex ASCII char and the valid. However, the valid was removed in the final implementation, as it was used mainly just for sort of testing and simulation. Now we have also our intermediate registers, which is the 3-bit bit count, the dot prev, dash prev, which are the previous states of dot and dash to prevent the double counting, and the 6-bit Morse sequence. And first, upon initialization, we set all these intermediate registers to 0. And then we have one always block for the code. We initiate on pause edge clock or pause edge reset, and of course, like the standard practice, when reset is high, everything is set to 0, and it's all reset from the very beginning. And now here we always update the previous states to be the current state, which is dot and dash, and then we enter this loop if either dot or dash is high, and we enter this loop if dot prev and dash prev are both 0. And then here we shift the Morse sequence left, and then we append 0 for dot and 1 for dash. And we increment the bit count by 1, and valid is still 0. This is here mainly for if you're going from char end back to dot dash, so valid gets set to 0. And then once char end is pressed, we go through our sort of decoding. We filter by bit count first, so bit count 1, bit count 2, bit count 3, and so on. And then within each of the bit counts, we have a case statement for the Morse sequence. So as you can see, this means with bit count 1 and all zeros, this means 1 dot, which is an E, and 5 zeros and a 1 with bit count 1 is a dash, and so on. And then this is true for the rest of the code. Finally, everything is reset after decoding, and that's it. It's very simple. We prevent double counting, and everything is decoded in real time.
This is the ASCII ROM module for our project, and it essentially is just a library of bitmaps containing the patterns for different ASCII values. And so how it works is we take the address input, which is just the signal for the binary signal for a certain letter that is coming from our Morse decoder, and this specifies the location in ROM from which to fetch the data being the bitmap, and then the output is just the bitmap so that we can correctly display the letter on the screen. And on each positive edge of the clock, it just checks whether there is an address input and then sets that to the register address, which the following bitmaps depend on. This is the top module for our project, and it has the inputs reset, dot, dash, and character end from our FPGA buttons, as well as the input clock, and it outputs H-sync and V-sync, which allow proper syncing to the VGA cable, as well as the 12-bit RGB output for the VGA pixel colors. It also outputs LED on, which indicates whether a current VGA pixel should be active or inactive, or if it's shown on the screen. And it also outputs the 8-bit ASCII decoded character. Next, it instantiates a slower clock signal and the valid wire, which indicates whether the output is valid or not, or essentially if character end has been pressed. It also has a register for temporary storage for the decoded letter, as well as wires to control the VGA synchronization. It then connects the internal VGA sync signals, which are VGA H-sync and VGA V-sync, to the top level module outputs, which are H-sync and V-sync. Then it instantiates a clock divider module and generates a slower clock. After this, it instantiates the Morse Decoder module using the new slower clock, as well as all the inputs from the buttons from the beginning, and what outputs the ASCII character, as well as the valid output. Next, there's an always block that latches the ASCII character from the decoder into the letter register when character end is high and valid is high. And when reset is high, this just resets the letter to 0. Next, it instantiates the VGA controller, which is responsible for managing the H-sync and V-sync signals, displaying the ASCII character on the VGA screen, and outputting the proper LED on signal. And finally, there's just an always block to control the color of the letters and the background. So if LED on is on, it sets the pixel color to white, and therefore those are the letters, and otherwise it sets it to black, making that the background.
Hi, this is Parth, and I'm going to be going over the ASCII test module. So the purpose of this module is that it's designed to render ASCII characters onto the VGA display. Here we have our inputs, our clock signal, our video on signal that's indicating whether or not the VGA is currently active or not, our X and Y's, which is the current pixel coordinates from the VGA controller, and then ASCII add, this is for the ASCII code for the character to be displayed, and then our output RGB, which is a 12-bit signal representing the color of the current pixel, and then over here we have all of our signal declarations. And over here, we're instantiating the ASCII raw module that was described earlier, which was basically just a library for all of the ASCII characters. And then for ASCII ROM interface, over here, our assign char row equal to y, 4-bit y. It's extracting the lower 4 bits of this coordinate to represent the row number within the ASCII characters bitmap, and it's doing the same for here. It's extracting the lower 3 bits of the x coordinate to represent the column position within a single row of the ASCII characters bitmap. And then all the way here on the bottom, this is what's helping display each of our characters, where once the video signal is on, it'll display a blank screen. And then once the signal for the ASCII bit on turns on, it'll display each character in black letters and leave the background in white.
Hello, we're going to be going over the VGA control module. So up here at the top, we have 2 inputs. One is the 100 megahertz clock signal coming from the FPGA, and then we have the reset signal. So if the user wants to reset the display, then this is where it'll be inputted. Then we have a load of outputs, which we will go over later on in the code, but just to quickly go over, we have the video on, which tells us when a pixel is turned on or off, the horizontal and the vertical sync, the 25 megahertz clock frequency, and then the x and y coordinates of the pixels. Now down over here, we have defined the display of the VGA to be 640 pixels horizontally and 480 pixels vertically. So over here, we can see our clock divider. The FPGA gives our program a 100 megahertz clock frequency, but for the VGA, we need a 25 megahertz clock frequency, and that's what this segment over here is supposed to do. The counter increments on every rising edge of the 100 megahertz clock, and when the counter resets to 0, the variable signal asserts for 1 out of 4 cycles, effectively creating a 25 megahertz pulse. Down over here, we have the horizontal and vertical count registers. So that's over here, and then we have some additional buffers, and we have 2 of each kind of buffering just to make sure that we're avoiding as many glitches as possible. So down over here, we have the register control, and pretty much the register control is responsible for managing the state of the key registers, and it is updated with the clock frequency that we've given it. Down over here, we have the logic for the horizontal and the vertical counter. So the way that these 2 counters work together is the horizontal counter increments with every clock cycle going to the right and displaying a new pixel. And then once the horizontal counter gets all the way to the edge of the screen, the vertical counter increments by 1 and then pushes it to the next line or the next pixel down. And then it continues on like that. And then these 2 lines over here just make sure that the program and the horizontal and vertical sync are triggering when they're supposed to be triggering and in the correct place. And then this video on and off is what really does a lot of the magic. So what this does over here is tell the program whether the pixel should be turned on or off at that specific location. And that's how it draws everything onto the screen. And then at the very, very bottom, we assign all the data that we generated up here to its respective outputs so that the rest of the program can receive these numbers.